should be recording. So for those of you who just joined, I put the gist code on the calculator there. So I'm going to switch. I mean, if it's a bit annoying, then I will turn it off at some point later. Okay. So as I mentioned, I'm going to continue about the turn maneuver or turning maneuver, because last time we already discussed about one of the pull-up maneuver, which is one of the other type of maneuver that usually the aircraft do, and then obviously you are aware that a very extreme maneuver, whether it is the pull-up or the turn, for this one, for example, you're going to see that in extreme conditions, not all the aircraft could do it or allowed to do it, because for example, like if you design commercial passenger aircraft, such as what you are designing at the moment, doing these extreme maneuvers obviously is not possible in a way that we talk about, like VN diagram, the flight envelope, for example. If you do, if you pull quite a high G load or G force or N, then obviously it's going to first of all, it's going to upset your passengers. It's going to upset the people inside of your aircraft, obviously, and then obviously further than that, it's going to now start, you know, affecting your structural, for example, structural limit, sorry, and then also the aerodynamics limits of your aircraft. So now this is one of the maneuvers that I'm going to speak about today. I think it's better to put that in the previous slide, which is that should start with this. Yes. So there are different type of turns, which is the first one is obviously the skid and slip turns, which I'm going to talk about that later on. But of course, a very kind of like raw turn maneuver is what they call it uncoordinated turn, which is obviously the turn that you were doing with your aircraft due to for example, the side slip effect, the side slip angle happens to your aircraft. Now we already discussed a bit about the at first yaw and at first roll. I hope that you still remember that. So if I could just turn on my camera. Obviously, when you do the turn like that, then for the conventional aircraft such as this, then what happens is that one side of the wing will have more drag than the other side, because as we understand that if you increase if you turn, then one side of the wing will increase the lift, and then one side of the other wing will decrease the lift. That's why then that turns happen, right? So doing that by deflecting your aileron control surfaces. So now we know that CD is a function of CL, right? So in your drag polar equation, you know that CD equals CD naught plus KCL square. Then if CL increase, then your CD is also increased. Now, if you increase one side of the wing, the CL increases one side of the wing, by default, you also increase the drag of that side of the wing. Then what happens is that one side of the wing will also suffer or will experience more drag than the other side of the wing. That makes that one side will slightly, have more drag, slightly push backward compared to the other side of the wing. Now, rather than only having a poor turn like this, then you also have kind of like a yaw. That's what we call it an adverse yaw. So I hope you get that point where we talk about that. That then what we call it, if you don't coordinate that is what we call it uncoordinated turn, right? That's why for a big airplane, a modern airplane, that could be done through a computer. So a computerized actions are already been pre-programmed, for example. So when you turn, at the same time, the computer will command the rudder, the back, to compensate that, or to counteract that balance of that yaw movement. Okay. Now that slightly a bit more challenging if you fly like a non-modern aircraft, such as a small aircraft, such as Cessna or Piper or Bulldog, and obviously you have to do it yourself. If you're a pilot, you have to kind of like coordinate it yourself with, once you turn, then you have to also slightly push your rudder pedal in order to then make a compensation. So your turn will kind of like slightly coordinated turn, right? So that is what actually most passenger aircraft, the coordinated turn is that what you want, right? So you want your aircraft slightly bang like that and then make a completely turn. For example, if you want to turn your heading like that. Okay. Now the good thing is that, or the best possible of coordinated turn is that you keep your how do you call it, the altitudes always level. So if you initially in that kind of altitude position, for example, and then when you turn, you want your aircraft steady in the altitude all the time. So what you do is just you turn your well, directions of the aircraft. Obviously, that's what the intention for you to turn, to change your direction. So when you turn it, then your aircraft is always stay in the same level of altitude. So it's not going to go up or it's not going to go down. Now that comes to the point when we talk about slipping and skidding, right? So I hope you get the point of what actually the intention of having a coordinated turn compared to the uncoordinated turn, the one that is obviously, for example, you have also the yaw motions. The same thing happens when you do the change your direction by changing your rudder at the back. Right? Changing the rudder at the back, you are hoping that that rudder actually produce side force, which that side force actually then turn the head or the point, the nose of your aircraft to either to the left or to the right. But at the same time, obviously, because you have a vertical fin like this, the acting point of that side force, which obviously have a distance to the CG, which normally inside of your fuselage, that distance between the acting force to your CG obviously will make your aircraft is also roll, right? Because of that. So rather than having only a pure, changing the nose direction, you also have the roll at the same time. So that what we call it the adverse roll, the one that I'm talking about before, about the increasing lift and then decreasing lift at the other side of the wing. That is what we call it an adverse yaw. Okay, so now obviously if you are a good pilot, a commercial pilot, you want that is not going to happen when you do the turn. So you want that completely coordinated turn with the high altitude, well, the level of altitude constant, and then you do a coordinated turn like that until you kind of like reaching the directions that you want. For example, if you want to make a 180-degree turn, obviously you want to do like that, and then you want that aircraft slightly move and turn and until you reach kind of like 180-degree change of heading. Okay, so that is we call it uncoordinated, well, coordinated turn with the or steady turn. So that is the last point in there. Now the skid turn is obviously the one that happens when you change your altitude. Right? So skid turn and slip turn, slip turn, sorry, is the one that when you drop your altitude. So if I could just put it again. So if you change, if you make a turn like that, then slip is when you drop the altitude rather than keep your altitude level, then you kind of like drop it. So that is always happen if you're not making a coordinated turn, or if you turn with a quite relatively higher velocity, then what happens is that your aircraft is actually skidding. So it's kind of like, well, just like, for example, if you make a turn with your car, if you're going too fast, then obviously your aircraft will skid. Rather than make a turn, it's going to slightly going forward, which obviously is quite dangerous for if you drive a car. Obviously, is dangerous, but of course, if an aircraft that is then we call it inefficient turns or a slip or or skid turn. Now, fortunately, on the cockpit, in the cockpit, usually on your flight deck, and there is an indicator. They call it a turn and side slip indicator, which looks like this, which is quite old version of this is the manual one. But of course, if you are familiar with the electronic flight instrument systems, it is usually integrated with the FIS, the VFD, the primary flight display, which usually shows at the bottom of the VFD, which is also more or less representing the ball rolling. So if you make a turn, for example, indicated by your artificial horizon and your icon of your aircraft, such as this examples, then that ball, if you skid, then that ball is going to move slightly outside of that box there. If you make a slip, then that that ball is going to go the other side, or the other way. So that is a tendency to side slip, or you make a skid turn or slip turn that could be kind of like noted by the pilot if they pay attention to that to that slip turn and side slip indicator there. Okay, right. So now if you make an uncoordinated turn, then by default you kind of like producing a side force, because when you do the turn, then your aircraft is going to make a side force. Either if you have like if you are skidding, then your side force is going outward, which is the centrifugal force. Now if you make a slip, then your aircraft is going to lose the altitude, and then obviously that is force is obviously becomes your centripetal force, right? So now that basically could be indicated from the equations that we have already seen. So I'm not sure whether if I could just turn this slightly to change it to, let me take that off. I hope you could already know the GIS code, so I'm just going to switch it off. So if you go to, if I could just change it to my whiteboard. Right, so the one that we're talking about is obviously the third one. If I could just draw that, which is this equations. You've seen these equations already. I think if you flip through back to the slides, the first equations here, sorry, the third equation there, would we say that if you want to have an uncoordinated turn, obviously happens because of the side slip, so that where is no roll angle, so obviously that becomes 1, like, so if I, that becomes 0, so if I just write it down, L sine theta minus S cos theta there, MV d psi, sorry, dt. Then if we have the turn, uncoordinated turn, where bang angles not happening, or bang angle equals 0, then that becomes 0, right? Because sine pi, if pi is 0, then sine pi is 0. Then cos pi is obviously cos 0 is 1. So you all you have is basically end up with S equals mv. Now I'm going to change that d psi dt into psi dot, right? So then the psi dot is become rearrange the equations. That psi dot becomes S divided by mv. Okay, so that is what actually what you have seen on that slide, which is that one. Okay, so that is your variations obtained by the side force S. Okay, now obviously the side force mainly produced by your rudder deflections rather than making it by the rudder, sorry, aileron deflections. Okay, so that is an uncoordinated turn. Now the skid and the slip turn, obviously I think physical meaning of that we have already discussed. So skid happens when the bang is less, a net side force act towards the center of the turn, then and the aircraft will skid. So the ball, the turn and side turn indicators, the indicators that we have already discussed, indicates by moving the opposite directions of the turn, but the right bang angle is shown by the aircraft symbol. So if you look back to that indicator, turn and side slip indicator, then obviously when you make a turn, that aircraft symbol there is going to make like that. For example, that actually shows your bang angle. But if you make a slip or skid, then that ball is going to move to the side, or to the left side or to the right side. Okay, now I guess I just probably make you aware. So if you do your flight sim assignments, when you try to make a coordinated turn, I think there's one of the I read that's one of the Johnny asked about for you to handling qualities, for example, like bang hold. So what you are asked actually to make a coordinated turn by banking your aircraft in a steady flight like that, in steady altitude. Then obviously when you do that, and you need to make sure that you don't drop your altitude by looking at the side slip indicator, turn and side slip indicators that we talked before. So try to make sure that when you make your model, try to put one of that instruments on your flight deck in your cockpit, so you can see actually the how much that you drop, or well, you should not drop, or you should not actually increase your latitude. Okay, so I think that is the skid and slip. So obviously the slip is the opposite of what happened to the skid. So when the bang is slightly more, then the net side force act outward. So then the aircraft will obviously slip, and the ball actually move in the directions of the turn. So that is the right bang, and then the right bang angle is shown by the aircraft symbol. Still, your bang angle was shown by how much your wing actually tilted upward or downward, for example. But the slip and skid will be shown by the ball in the middle of that kind of like pendulum type tunnel. Okay. Right, so I think there's a picture here showing that. So when you have the skid, your aircraft, obviously the roll angles is showing in that directions, but of course then if you make a skidding turn, then that ball is moving to the opposite, well, to the same side of your rolling wing. But if you make a slip, then your aircraft is obviously have a roll angle like that, but then the ball is moving to the side of where your wing part is reduced or downward. Okay, so that is just a couple of pictures showing you how what happens if you do the slip and the skid turn. Okay, now if we talk a bit more about the bang turn, obviously is you could obtain it through the bang rotation. So the yaw variations depend on the side force and the lift, and the flight path angle will have a variations unknown. So now remember, when we talk about pull up last week, then the flight path angle is what happens to your, if I could just put my camera on, what happens is that if you turn, then if you also pull up like that, then that is when your gamma is not equal to 0. But if you keep your nose always down like that, steady in the same altitude, then obviously your gamma is going to be 0, right? So that equation there, which is coming from the the same equation. So if I just turn again to the first equations that coming from that first equations that you have seen in the, I don't know what slides number, but if you flick through back to your lecture note, you will see the equations that we derive from the second Newton law. Okay, so if you put it like that, then equate that to 0 because there is no variations of flight path angle, then you have that kind of like equations. Now remember, when we talk about this, obviously, initially when you fly in a steady level flight like this, and then suddenly you want to make a turn, then there will be a consequences of that. The consequences of that, there will be a changing in the load factors of your aircraft, because now you know that your lift is no longer pointing vertically upward. When you make a turn, your lift is going to go pointing in that direction, which obviously will then have a consequences. The lift that need to compensate the weight, which is the weight is obviously always pointing downward, is going to be reduced, right? In order to do that, you have to do something. Now, to do something, it either you increase your speed, then you increase the lift, because lift is actually a function of your airspeed, right? Lift equals half rho v square s cl, or you could then also increase the thrust. So that is why to maintain a sustained level turn at a given velocity, if you want to keep your velocity constant and a certain bang angle, then the thrust must be increased from a straight level flight. Initially, for example, you put like a 60% throttle setting. When you make a turn, when you want to make a coordinated turn, then you have to do with the thrust. If you don't want your, if you still want, if you don't want to increase your airspeed, so either increase the speed or you put the throttle slightly higher, because eventually you know that the lift to compensate the weight, which is always pointing downward, is going to reduce. Then in order to do that, you have to put the thrust slightly. We're going to look at that in a bit more detail in terms of equations on the previous slide, sorry, on the next slide. Okay, right. So we know always that now we start talking about steady turn now, which is the level coordinated turn. So obviously we always know that the load factors always L equals divided by weight. Then if you make a turn like that, then obviously that it becomes a function of your bang angle. So if I could just draw one of the equations of that aircraft, and obviously you have your weight pointing downward, right? So initially your aircraft, if I could just use a different color, initially when you fly in steady level, that is your wing is going to go like that, right? And then obviously that is your fuselage, that is your vertical tail, say that is your horizontal tail plane. Not sure why it's very sensitive in this, but I hope you will bear with me. But when you turn, then that aircraft becomes like a red aircraft there. So your wing is going to be like that, and your vertical tail, then your horizontal tail. I think it's better not to draw it, just to not to make it that crowded. Then obviously that becomes your bang angle, right? Pi. Now initially the weight is always pointing downward like that, but initially in the green in the green aircraft, when you steady level flight, your lift always compensated by the lift. Your weight is always compensated or always balanced by the lift over there. But because you make a turn, then your lift is going that way, right? Now, obviously, to compensate the weight, then you have to, it has to be done by the component of the lift in that directions there. Now, if there is a bang angle there, then obviously that lift is going to be reduced, right? So that is why we talked earlier. Then, in order to compensate that, you need to increase your throttle in order to make a thrust. But in here, obviously, if we before we agree that actually the load factor is lift over weight, then because that becomes your then that is pi, right? So then this component here is your lift cos pi, right? So then lift cos pi has to be equals, right? Lift L cos pi has to be equal to weight in order for you to keep steady in the, you're not dropping any altitude, right? So if you keep the altitude always level, right? So then that lift cos pi equals weight or W, then obviously if you put that L, so weight goes to the other side, and then cos pi goes to the other side, then that becomes that equation there. So now you can see, I put an illustration there. The bigger the pi, the bigger the bang angle, you could see that the bigger also the load factor, right? So if you have like well, obviously when pi equals 0, steady level flight, n is equals 1, but 30 degree, you start increasing to 1.2, 45 becomes 1.4, and then 60 degree, you already double the load factor, you already double the g-force, and obviously a 60 degree, you have like more than 2 g-force, which is, I think it's 75 degree, you have like 3.9 g-force there. Now, what happened? Probably you then ask, okay, what happened if you got like a 90 degree turn? Obviously, well, it is possible, and then you probably have seen it in the aerobatic airplane or fighter airplane. But of course, now you don't have any lift to compensate the weight because the weight is always pointing downward like this. I think I better to put my camera so you can see what I'm talking about. So if you like a 90 degree bang like this happens on, well, the aerobatic or fighter airplane, but obviously the weight always pointing downward, but the lift is going perpendicular to the weight. Now obviously there is nothing to compensate the weight in there. Now what happened is actually then you only rely on the speed of your aircraft. Okay, so you have to make a very fast turning in order that turn becomes to create what they call it centrifugal force, mv squared divided by r, right? Which is r is your radius of turning. Then that becomes, how do you call it? Like I don't know whether you have heard about the trick that you want to lift kind of like a marble or a small ball without touching it. I don't know whether you know that trick. You put the ball on the table, for example, if you want to impress your date. How I can lift that ball, little ball, without touching it. Obviously, you put like a cup, upside down cup to cover that ball or that marble, and then you start rotating it until that ball is actually rotate inside with a certain kind of like rotation of your hand, and obviously that ball is start to spinning inside of that cup, and then obviously you could then increase that ball up without having to touch it. Well, you touch the cup obviously, but you don't touch the ball or the marble, but you eventually you could just leave it up as long as you keep rotating it, and you can leave it out and move it somewhere else. For example, if the trick is to move this ball from one place to the other place. Okay, so that is happening, but as you can see, mathematically it's impossible, right? Because of what? Because of that equation there. Because you know that if pi 90 degree, you know what cos pi is? 0, right? So cos pi is 0, is cos 90 degree is 0, then if it is cos pi or cos 90 degree is 0, then 1 divided by 0 is infinity, not a number, right? So that would be a very high load factor. That's why I think the maximums, well, the maximums load factor that could be sustained by the passenger aircraft usually no more than 60 degree, obviously. Well, you should not do that anyway, because then 60 degree, as you can see from that illustration, if you bang your aircraft in 60 degree, you double your G-force, right? Which is NZ becomes 2 now. Initially, you have 1 G, which is the one that we experienced, which is equals to 9.81 meter per second square. Right, that's the G force that you always experience in day-to-day basis. But when you bang your aircraft 60 degree, then you double that G force, and you feel like you kind of like sink to your seat more than the weight of your body, right? So that is the connections between the bang angle and the G force or the load factor from that equation there. Okay, right. So now, obviously, if you execute it coordinatedly, or then obviously this is what we should see on your turn and side slip indicator. So your aircraft banking like that, right? But your ball stay. I mean, the indicator ball indicator is kept in the middle of that. Okay. Now the turn radius, as we know that if you look at, obviously, if you look at the aircraft from the front view, is going to be like that. But if you look at from the top view like that, then if you have a make up a steady turn, then you will see if that is, if it's a good pilot, for example, sorry to draw it like here, then your aircraft initially over there, for example, from the top view, sorry about that, that's your horizontal tail plane from the top. Gosh, sorry. And then at this side is going to be that position there, right? This is your wing. In that positions, and then obviously if you turn it 180 degree, it's going to be that way. And then if you over here, that's your aircraft, that is your wing, that is your nose, that is your tail. I think I slightly changed the sensitivity of my tablet, that's why it becomes like that. So it's come like that. So I hope you understand that if you look at from the top, that is what's happening. Obviously now that is what we call it pi dot. Okay, then that pi dot is basically, if you are flying with a v, the velocity, that pi dot is actually v divided by r, which is r is your radius of turning, right, or the turn radius. Right now, if you then try to make connections for this steady turn, then in steady turns, obviously there's no side force. Otherwise, the ball in the turn and slip in the side slip indicator is going to move slightly, well, not stay in the middle, but it's going to move to the left or to the right. So if you keep that side force is very small or considered 0, so you could then think about L actually much greater than S, which is your side force. Now from the previous equations, then you could then obtain this kind of like connections between the pi and the velocity and your on your radius of your turn. Okay, so if I could just go back to what I think this, which is I obviously already put it here. So to arrange that, that is the equation that we've seen before, right, on the slide. Then if you think that there is no side force, or is considered that your lift is much greater than the S, then obviously if you could just use the red and make it different, then obviously that becomes 0, right? No S. that is also become 0, right? Now we agree before already that gamma, if you want to make a steady turn, there's no gamma, there's no flight plot, so your aircraft knows it's actually stay level. Then that cos gamma becomes 1, right? So then you only have like this equation, which is obviously L cos gamma minus W, which is MV. Now, obviously that MV d gamma, because d gamma is also, there's no change, then that MV d gamma dt is also 0. Right? Sorry, I think I should put that into 0. I think just make a right. So that is become 0. Right. Then if you look at the third equation there, we know that there's no component in there as equals 0, then you have L sine pi equals mv d psi dt, right? So from this, obviously, this equation, then you have L cos gamma. I could just rewrite that and then move that W to the other side. Now, if I put this underneath here, L cos gamma equals W, right? Then if you kind of like, how do you call it, divide it, so L, the first, this equation divided this equation, you got tangent pi, right, sine over cos, and obviously you have, is it MV, which is MV d gamma dt, and then below is W, which is obviously mg, right? So you have that then over there. So you have V divided by G. Now d gamma dt is obviously sorry, d psi. Sorry, I probably mentioned the wrong notation. D psi dt, then obviously psi dot, right? So that is what you have in the equations there. Okay, so I hope that you get the point where we could get that. And then obviously now we know that from the previous statement that psi dot is actually V divided by R. Remember that? Then if we replace that psi dot with a V over R, then that is then becomes V square divided by GR. Right. So you rearrange it, rearranging that equation to get the R as a single term, then that is what you have. Okay, so I better go back to the slide. It's much clearer. Hopefully that you could get. So that is the rearranging of the R there, right? Okay, now with the definitions of the load factor on slide 24, which is L over W. Remember that L over W 1 cos gamma, and obviously that or which is NZ, right? And then 1 cos pi. Sorry about that. Cos pi 1 over cos pi is NZ. Now you put that NZ right at the bottom there, because obviously 1 over NZ from this equation, 1 over NZ is obviously cos pi, right? So if I change that cos pi with the 1 over NZ or N, then that is your R as a function of V, the velocity, functions of the bang angle, as well as also the functions of your load factor or g-force. Okay, now we know that using the trigonometric functions, sine square, you know that sine square pi plus cos square pi equals 1. That is the trigonometric equation. Then you could make rearrange sine pi becomes square root of 1 divided minus cos pi square. Then obviously you could then change that equations into a different form of equation. It's simply to remove the pi, so you can see that that is a function of the radius, is the function of the aircraft velocity, the g, which is the gravity accelerations, and your load factor or g-force. Okay, now The two equations actually tells you something. Now, if you talk again about the pi dot, sorry, psi dot, which is omega, you know, the turn, the angular velocity from from this illustration here. So if you make a turn 180 degrees like that, then obviously the pi dot is this, right? So if you change that um, uh, to the equations that we have previously, which is r is there, then you have the turn radius or psi dot is g square root of n square minus 1 divided by v. Now this equation and the equations before, which is this one, or sorry, this one, the first one is actually tells you a lot about how you want to do your maneuver. Obviously, it depends on what aircraft you're flying. If you're a pilot, if you're a commercial passenger pilot, then obviously the limitation or constraints to you do the turn is obviously limited by the g-force. Right? But if you're a fighter pilot or the aerobatic aircraft, for example, pilot of the aerobatic aircraft, now you want or you need to be able to turn in a short time. Obviously, if you want to kind of like beat your enemy in a dogfight or to have a better air superiority, you want to do the turn in a very short time and a very short distance as well. So it means that you minimize the R, right, to minimize the radius of turn. Now, if you could do that as much as possible to minimize the R, now obviously the rate of turn, which is what we have seen in these equations, obviously need to be quite quite big or quite maximum. So that's why to achieve either a tightest turn or a fastest turn, so the fastest omega dot or the smallest r, if you are a fighter pilot, that's what you actually want to do. Is basically you could do that by to increase your load factor. How? Obviously, you see from this equation, to increase the load factor is to increase your bang angle, right? So you will do the kind of like the fastest turn for your fighter aircraft is if you do it in quite a bigger roll angle, right? A bigger pi, because when you make a bigger angle, for example, like 45 degree, then you increase your ends to 1.4. If you make it like 60 degree, you increase your n to 2. If you do it in 60 degree, you increase your pi, sorry, your nz into 3.7, for example. So if you go back to this equation, then if you want to do it as quick as possible with the tightest turn and the fastest omega or psi dot, then you increase this n by increase the roll angle. Or now you can see that that is simply kind of like quite the opposite of how do you call it, the opposite of the logic that you could do it by slow down your aircraft, because it says the lowest possible velocity. This is what happened in your commercial passenger aircraft, because when you do a commercial passenger aircraft, you can't increase your n because you don't want to upset your passenger, right? As we know that increasing into a 60 degree, you have already doubled your g load or g force. Then what you could do is slow down your aircraft. So you want to make quite a turn by simply slowing down. Where's my camera so I could see that quite clearly. So what you do is usually if you've been in an aircraft, usually when your aircraft turn, they do it quite slow in order, first of all, to do it quite with the lowest or the smallest r, the smallest turn radius, with also with this relatively small g-force experienced by the passenger. Okay, from that equations that you could you could deduce from the equations over there. Okay, so I hope that is the point different between what you would do if you are a fighter pilot or an aerobatic airplane pilot compared to what you will do if you are a commercial passenger aircraft pilot, because different of the objectives are what you want to do it. Obviously, any pilot wants to do it very quickly anyway, right? So even if you are a commercial passenger aircraft, if you want to make a turn, 180-degree turn, for example, if you want to turn back to the airport that you just took off, for example, and then you want to turn it back 180 degree, you want to do it as soon as possible, as quick as possible, without with the fastest as possible that you could do. Now you can't make like that, because then you could increase the load factor, obviously, but you can't do it because you are limited with the load factor that you could put in the airplane for the passenger sake. But you could do it very slow. Then by doing it very slow, you can see that the R, the radius that you could achieve, is quite small as well. And then if you could make that turn radius is quite small, then you hopefully that you could make 180-degree turns faster, rather than compare it to, for example, you make it like a bigger R, for example. Okay, so I think if I could just then a few minutes, I'm going to talk about that, about the speed that you have to increase as well as a factor of load factor. I just want to make sure that we agree with that as well about right. Sorry. Yeah. So if you want to make a smaller R, then obviously here the equations I want to point out. If you want to make this small, and obviously you could slow down your aircraft, because if the small v, then obviously you got the small r. Okay, right. So now what happened to your velocity? What actually the necessary velocity when you do to make a turn, for example, then your velocity will change because we know that the L over W is your NZ. So if you put it the other side, W over there, then you got this equation, right? So now we know that L is actually half rho V square S CL, right? Then this is W and Z. So if you make V as a single term, then you have the equations over there, right? So you square root of 2 times, well, W divided by S, obviously. S, you could put it down there if you want, but since we want to see that as a single unit, which is your wing loading, right? Then you could write your equations like that. And you can see that is your load factor. Okay, now we know that in a steady flight, right, if the NZ equals 1, lift equals weight in the steady level flight, that you have already a speed, which is that one over there, right? So then if you change that equations, sorry, that terms, which I circle in red like that, as your initial speed when you do the level steady level flight, then you are end up with the square root of n load factor, and that it means that if you want to make a turn without losing any lift, then you need to increase your speed by the factors of square root of nz. Initially, you have a speed v0 in the steady level flight, and then you make a turn, then your speed have to be increased by the factors of square root of nz in order to make, you know, to keep your aircraft in steady level, in the altitude, level altitude. Okay, so I think it's about time. Now, probably I'm going to finish this, if it's not next week, just to sum it up, and maybe I will mention it as well in the tutorial. But next week I'm going to kind of like wrap up this turn, because I think we have quite a, well, only a couple of slides, but I don't think we have time to discuss it thoroughly today. So I'm going to leave it there, but I'm going to mention this 2 slides in the tutorial as well as also in the next week before we start talking about talking about the static stability. So next week, we're going to start talking about static stability. And the week after, we're going to talk about the handling qualities. I think that is what the contents of our materials for flight mechanics for this semester. I'm going to stop